Welcome to this scientific lecture on the focus-defocus cycle. Today we're going to explore one of the most fascinating phenomena in cognitive neuroscience: how switching between focused and diffuse modes of thinking triggers eureka moments. Let's start by defining what we mean by the focus-defocus cycle. This is a fundamental cognitive process that involves alternating between two distinct modes of neural processing. The focused mode involves concentrated attention directed at a specific problem or task. During this state, the brain activates highly localized neural networks in the prefrontal cortex. The defocus mode, also called the diffuse mode, involves a more relaxed state where attention wanders freely. This activates the default mode network, a distributed system across multiple brain regions. Here's a visualization. The focused mode shows concentrated neural firing patterns, while the defocused mode shows distributed, wandering activation. The cycle involves moving back and forth between these states. Now let's dive into the neuroscience. What's actually happening in your brain during each of these modes? During focus mode, the dorsolateral prefrontal cortex shows high activation. This region is responsible for executive function, working memory, and directed attention. Neurotransmitters like norepinephrine and dopamine increase during focused attention. These chemicals enhance signal-to-noise ratio in neural circuits, allowing precise processing. During defocus states, the default mode network activates. This includes the medial prefrontal cortex, posterior cingulate cortex, and angular gyrus. These regions are associated with mind-wandering and spontaneous cognition. Acetylcholine plays a crucial role in the defocus state. It modulates cortical plasticity and allows for broader, more associative connections between distant neural networks. Here's an important question. If focus mode is so effective for problem solving, why can't we just stay focused all the time? Why do we need to defocus? The answer lies in the limitations of focused attention. When we focus intensely on a problem, we create what neuroscientists call functional fixedness. Functional fixedness is a cognitive bias where we become trapped in a particular mental set. Our neural networks become entrenched in specific patterns, preventing us from seeing alternative solutions. In focused mode, we search a narrow region of problem space. In defocused mode, our mind explores a much broader solution space, making unexpected connections. Now we arrive at the central question: what triggers a eureka moment? How does the focus-defocus cycle lead to sudden insight? Research shows that eureka moments often occur during what's called an incubation period. This is a phase where you step away from active problem solving. During incubation, unconscious neural processes continue working on the problem. The brain performs massive parallel pattern matching across distributed memory systems. The eureka moment occurs when previously unconnected concepts suddenly link together. This happens when the default mode network finds an unexpected association. Imagine known concepts A, B, and C in your memory. During defocused mode, the brain discovers an unexpected connection between C and the solution X. This is the eureka moment. What does the scientific evidence tell us? Let's look at actual brain imaging studies that have investigated this phenomenon. A landmark study by Kunios and Beeman in 2009 used functional MRI and EEG to study insight moments. They found distinctive neural signatures just before and during insights. Just before an insight, they observed a burst of high-frequency gamma waves in the right anterior temporal lobe. This region is associated with making distant semantic connections. They also found increased alpha wave activity in the right occipital cortex about 1.5 seconds before the insight. Alpha waves indicate reduced visual processing, suggesting internal focus. Gamma waves oscillate at 30 to 100 Hz. These high-frequency oscillations bind distributed neural assemblies together, enabling the integration of distant concepts. Alpha waves oscillate at 8 to 12 Hz. They're associated with relaxed alertness and internal attention, perfect for insight generation. Here's a practical question many people ask. How long should I focus before switching to defocus mode? Is there an optimal timing? Research on ultradian rhythms suggests that our brain naturally cycles through focus and defocus approximately every 90 to 120 minutes. This is called the basic rest-activity cycle. However, for deliberate practice, most research suggests optimal focus blocks of 25 to 50 minutes, followed by brief defocus breaks of 5 to 15 minutes. The popular Pomodoro technique of 25 minutes focused work followed by 5-minute breaks actually aligns well with these biological rhythms. It's not arbitrary. It's based on how attention naturally fluctuates. This diagram shows the classic pattern: 25 minutes of focused work, followed by a 5-minute defocused break, then back to focus. This rhythm optimizes both concentration and creative insight. We cannot discuss the focus-defocus cycle without addressing sleep. Sleep represents the ultimate defocus state and plays a crucial role in insight generation. During REM sleep, the brain performs memory consolidation and integration. Neural connections are strengthened, weakened, or reorganized based on the day's experiences. Research by Wagner and colleagues in 2004 showed that sleep facilitates insight by enabling remote association. Subjects were twice as likely to solve insight problems after sleep compared to an equivalent wake period. Slow-wave sleep, the deepest stage, implements synaptic homeostasis. This process scales down synaptic connections, removing noise and highlighting signal. It's like defragmenting a hard drive. Another important practical question: what specific activities are best for entering the defocused mode? What should you actually do during breaks? The key is engaging in low cognitive load activities. These are activities that occupy your attention lightly but don't require intense focus. Walking is particularly effective. Research shows that bilateral rhythmic movement, like walking, enhances connectivity between brain hemispheres and promotes creative thinking. The famous shower effect is real. The combination of relaxed alertness, warm sensory input, and white noise from water creates ideal conditions for insights. Many people report Eureka moments in the shower. Meditation, especially open monitoring meditation, trains controlled defocusing. It strengthens the ability to switch between focused and defocused states at will. These are the 4 most effective defocused activities backed by research: walking, showering, meditation, and light exercise. All promote the neural conditions for insight. Can we mathematically model the probability of insight? Researchers have attempted to quantify this process. The probability of insight is a function of incubation time, the number of activated concepts, and the spreading activation coefficient between concepts. The spreading activation follows an exponential decay with distance d between concepts, where lambda is the decay constant and k is the coupling strength. Longer incubation periods increase insight probability, but with diminishing returns. There's an optimal window, typically hours to days, not weeks. The more concepts you've activated during focused work, the more potential connections exist during defocus processing. This is why focus preparation is essential before defocusing. It's important to discuss when this cycle fails. Not all defocusing leads to insights, and some practices can actually harm the process. Digital distraction is a major problem. Checking social media or emails during breaks doesn't allow true defocusing. It engages focused attention on trivial matters, preventing the default mode network from activating. Chronic stress impairs the ability to switch modes. High cortisol levels keep the brain in a vigilant, focused state, preventing relaxation and the insight-generating defocus mode. Insufficient sleep is devastating for the focus-defocus cycle. Without adequate sleep, memory consolidation and neural reorganization cannot occur properly. The solution is to protect break time as rigorously as you protect focus time. Turn off devices, avoid stimulating content, and engage in genuine recovery activities. Let's look at how this cycle applies across different domains. The focus-defocus principle is universal. Henri Poincaré famously described his mathematical insights occurring during walks and while boarding a bus. Einstein reported similar experiences, with relativity insights coming during daydreaming. Artists described their creative process as alternating between intense focused work and periods of stepping back. Beethoven took long walks where musical ideas would come to him fully formed. Athletes use defocused visualization during rest periods. This mental rehearsal, done in a relaxed state, improves actual physical performance through neural pathway strengthening. Final question: can we actually train our ability to leverage the focus-defocus cycle? Or is it just something that happens naturally? Yes, absolutely. Like any cognitive skill, you can train your ability to focus deeply and to defocus effectively. It requires deliberate practice and awareness. Start with shorter focus intervals, perhaps 15 minutes, and gradually increase duration. This builds your concentration stamina, similar to how you would train physical endurance. Practice structured defocusing. Set a timer for 10 minutes and deliberately let your mind wander without digital devices. This trains the switching mechanism. Develop metacognitive awareness. Notice when you're in focused versus defocused mode. This awareness itself strengthens your ability to switch between modes intentionally. This shows a progressive training protocol. Each week, gradually increase your focus block duration while maintaining quality. This systematically builds your cognitive endurance. Let's dive deeper into the neurotransmitter dynamics that underlie mode switching. Understanding the chemistry helps us optimize the cycle. Dopamine concentration during focus mode is greater than during defocus mode. Dopamine enhances signal detection and maintains attention on task-relevant information. Conversely, acetylcholine levels are higher during defocused states. Acetylcholine promotes cortical plasticity and enables the formation of novel associations. The key insight is that neither extreme is optimal. Pure focus without defocus leads to rigidity. Pure defocus without focus leads to incoherence. Balance is essential. Why did this dual-mode system evolve? Understanding the evolutionary context illuminates why this mechanism exists. The focused mode evolved for immediate threat response and precise action. Our ancestors needed intense concentration when hunting prey or avoiding predators. The defocused mode evolved for environmental monitoring and creative problem-solving. During safe periods, the brain could explore possibilities and make long-term plans. The modern mismatch is that we now face constant demands for focused attention, with little time for natural defocusing. This is evolutionarily novel and cognitively expensive. Let me give you a concrete, evidence-based implementation strategy you can start today. Step 1. Audit your current pattern. Track one full day, noting when you're in focused versus defocused modes. Most people are shocked to find they rarely truly defocus. Step 2. Schedule defocus time as seriously as you schedule meetings. Put a 10-minute walk on your calendar after each 45-minute focus block. Step 3. Create environmental cues. Have a dedicated defocus location, perhaps a comfortable chair or a walking route. This trains your brain through context-dependent learning. Step 4. Physically remove digital devices during defocus periods. The temptation to check them will undermine the entire process. Step 5. Keep a Eureka journal. Note when insights occur and what you are doing. Over time, you'll identify your personal optimal conditions for insight generation. Let's examine specific cases of scientific breakthroughs that demonstrate this cycle. Auguste Kekulé discovered the ring structure of benzene during a daydream about a snake eating its tail. This came after months of focused work on the problem. Archimedes discovered the principle of buoyancy while relaxing in a bath. The focused preparation was his prior work on density problems. The insight came during defocused relaxation. The pattern is clear. Focused preparation loads the problem into memory. Defocused incubation allows unconscious processing. The insight emerges when you're not actively trying. This timeline shows the typical pattern. Extended focused work loads the problem. Brief defocused state allows reorganization, and the Eureka moment emerges at the transition. Can we quantify insight quality and frequency? Researchers have developed metrics. The remote associates test presents 3 words and asks you to find a 4th word that connects them. Performance on this test correlates with real-world creative achievement. The alternate uses task asks you to generate unusual uses for common objects. This measures divergent thinking and benefits from defocused processing. One proposed insight score equals the number of novel solutions divided by time to solve, multiplied by solution elegance rating. This captures both speed and quality. The focus-defocus cycle actually changes brain structure through neuroplasticity. This is not just a temporary state change. Focus practice strengthens specific neural pathways through long-term potentiation. Neurons that fire together wire together, building expertise in particular domains. Defocused rest enables synaptic pruning, removing unnecessary connections. This is essential for efficiency and prevents interference between memories. The alternation between building and pruning optimizes overall network architecture. You cannot build without pruning. and you cannot prune without building. Not everyone experiences the focus-defocus cycle identically. There are important individual differences. Your chronotype matters. Morning people show peak focus in early hours and benefit from afternoon defocusing. Evening people show the opposite pattern. Individuals with ADHD show altered switching dynamics. They may defocus more easily but have difficulty sustaining focus. However, they often show enhanced insight during hyperfocus periods. Age affects the cycle. Older adults may need longer focus periods but show richer associative connections during defocused states due to greater knowledge bases. The key message is that optimization is personal. Track your own patterns, experiment with timing, and find what works for your unique neurobiology. Let's synthesize everything we've covered into actionable insights. First, the focus-defocus cycle is not a productivity hack. It's a fundamental biological rhythm rooted in brain architecture and neurochemistry. Second, both modes are essential. Focus without defocus leads to functional fixedness. Defocus without focus leads to unproductive wandering. Third, the switching itself is crucial. Eureka moments occur at transitions when the default mode network makes unexpected connections between focus-primed concepts. Fourth, you can deliberately train this ability. Progressive focus building, structured defocus practice, and metacognitive awareness all improve performance. Fifth, protect both modes from digital interference. Constant connectivity prevents true focusing and true defocusing, undermining the entire cycle. As we conclude, consider this. Your most valuable insights are not forced into existence through sheer willpower. They emerge from the dance between focused preparation and defocused incubation. The Eureka moment is not magic. It's the result of your brain's sophisticated pattern-matching architecture. Respect the rhythm. Trust the process. When you focus intensely and feel stuck, step away, walk, shower, sleep. Your brain continues working, making connections you cannot consciously force. The most profound truth: your best ideas will come when you stop actively trying to have them. This is not laziness. It's sophisticated cognitive science. Thank you for your attention during this lecture. I encourage you to experiment with these principles and observe your own Eureka moments. Science is not just about understanding. It's about application.